Hey everybody, welcome to QuickSilicon, and this is the introductory video on using System Verilog for design. Through these series of videos, I'd be covering various System Verilog features which are useful for designing, and as usual, alongside with this particular video, you'd be able to write the RTL for the particular concept which I'd be explaining and run it on the QuickSilicon platform. So before we look into the various language features which are essential for designing, I wanted to take out some time and talk about the basic element of building a particular block. So let's assume that you're designing this block, and what this particular block does is that it simply implements a simple 2:1 mux. And if you think about this particular block, what this particular block would be doing is that it would be getting certain inputs. Let's assume that since it is a 2:1 mux, it will get two inputs. Let's call them as A and B. And it would be producing an output. Let's assume that it produces the output called Y. Now, in most of the designs, the inputs A and the inputs B to this particular block would be coming in from a memory element. So you could assume that you have a memory element here, and this particular memory element could be either a flop, a latch, or even an SRAM. And if you think about it, it could even be an array of flops or an array of latches, which can be used for implementing a FIFO or a buffer. But in short, it would be coming out from a particular memory element and it would be driven to this particular block. So in design terms, this memory element is usually referred to as a sequential element. So once you get the input from this particular sequential element, you would have some sort of logic setting here to produce the desired output Y. Now, if you think about this particular output, it is nothing but a bunch of gates put together in order to generate the particular output. What your block is doing is it has a bunch of gates which are put together to form the desired output, which in this case is Y. And these set of gates together is what is known as a combinatorial logic. So this is what we call as a combinatorial logic. And what it basically consists of is either some of the universal gates or the NAND gates, AND gates, muxes, everything put together to form a particular desired output. For example, in this case, how your inputs A and B would be combined. So you'll have another input called the select. Let's assume that we get select also as the input here. And based on the value of select, what will happen is that you will produce the output which would be equal to either A or B depending upon the value of the select signal. So you will have the select line, and if the select is 0, you produce the output as A. If it is 1, then you produce the output as B. And this is what will be driven to the output Y. Now, we know that the inputs A and B were coming in from a memory element, and you had some sort of logic written here depending upon the select line, which will again be coming from a memory element. And depending on the value of the select signal, you gave the output as either A or B. And once the output is produced, in most of the cases it would go again and be written into another memory element. This could again be a flop or a latch or an SRAM. Now, once you have written your output into the memory element, this particular memory element would again be read out for the combinational logic which is present in the next stage to produce the next desired output. Now, if you think about it and put all of this chain of elements together, what you will get is a series of sequential elements or the memory elements, and between the series of sequential elements, you would have some sort of combinatorial logic setting which will be producing the desired output for every stage. So what it will look like is that you have a memory element here, some combinatorial logic, another memory element, and another combinatorial logic, and so on. Together, this entire thing will form a complex digital system which is supposed to work on certain inputs and produce the final end output. Now, in case of simple design, like the mux which we were talking about, you might not have any of the sequential elements playing a role because this particular mux would be part of this particular combinatorial logic sitting somewhere here inside, which is why it will just take certain inputs and then produce the output and be done with it. And you could have a single module which just does this. And the reason why you would have a module or a block for such a small design is to be able to use this particular block again and again instead of writing the logic whenever you need it. So that's why you would have this in a module. Now, given all of this information, what we basically need to do here in order to design a particular hardware is to be able to describe the sequential elements and the combinatorial blocks. So if we are able to have this defined and connected together, then we should be able to design most of the complex circuits. System Verilog actually provides you a way to describe these sequential elements and as well as this combinatorial elements. And you could then use the hardware description language to describe whether the sequential element would be a flop, a latch, or an SRAM, or even a FIFO or an array of flops or latches. Similarly, you could define the combinational logic to either implement an add, subtract, mux, or any other logic which you would want to implement in order to get your desired output. And this is how the System Verilog will actually help you describe this particular hardware by using various language constructs. Now let's take an example of how we would describe the mux by taking a look at the module and as well as the module definition. So if you were to design a particular module which implements a 2:1 mux, what you basically need is three set of inputs: input A, input B, and a select line. All of these are 1 bit, and you need to produce one single output, which is basically the muxed output between the two inputs A and B. In order to first do this, you need to describe this particular block, which in System Verilog is known as the module. And how you can do that is by using the module keyword followed by the name of the particular block. For this example, it would be mux 2:1. And then you can describe all of the inputs which your block takes. So here you would take three inputs, which is input A, B, and select, and produce one output, which is the Y output. Now similarly, what you can do here is once you have all of this information combined, you could simply drive your output by using a sign Y is equal to, depending upon the select signal, if it is equal to 0, then you would give the output as A, otherwise you would give the output as B. Now what I have done here is that I've used a ternary operator, and that particular ternary operator takes a look at the value of the select input. If it is equal to 0, then it produces A as the output, otherwise it produces B as the output and puts that output into Y. So what this particular code in System Verilog would do is it will synthesize into a 2:1 mux, where you would have the hardware described for implementing a 2:1 mux. And now in the next video, we would actually see how to write this complete logic in System Verilog and how we will test it with some test vectors.